Well, thank you. I'm very honored to be invited here tonight to speak about this topic. And I'm going to try to do about three things tonight. I'm going to try to, without going too far and too much into depth of the history, I'm going to look a little bit about the past, the present, and where we're really at, and discuss a few of the really pressing questions as we're going forward with adopting artificial intelligence into a variety of places in our society. All right, so without going too far back, this journey really starts with this concept of a computer. And of course, we all think now our iPhone, we think big servers and all this, but really some of the early devices that assisted us in doing computational tasks, the computer had very humble beginnings. But most of us know it as we've started to build things that are, controlled by pneumatic, controlled by electronics, and that thing still has less power than your iPhone. But we got bigger, we got more wires, the computer got a little bit more fancy, and then we made it small, we made it personal, we brought it to you. We made it sit in your lap and you could take it about wherever you wanted. And then we made it big again so that you could watch presentations like this, so that you could go onto Netflix and stream all of your favorite videos. But then now we're going back and we're making it small with quantum computing and trying to revolutionize the way that we can, the amount of information we can process and what we can do. But what you see is that the computer itself has drastically changed over the years. But what hasn't changed for the computer is that it kind of drew the short straw. A long time ago, the computer became something that just works for us, and it still is just something that works for us. If you're poor Wally out here, you have a task. That task is to go out there to find trash, compact trash. It is then to take that trash and stack that trash. Wally has a little bit of freedom in how he does it. He can change the path he does. He can change exactly probably if he wants to come around 90 degrees and pick up that little trash piece. But he works for us and he works off of our instructions. It's a very task-oriented thing. And this has been one of the tasks or one of the topics within computer science for a long time, is that really in the artificial intelligence and most of the stuff of how we worked with computers, we worked off this premise of algorithms. It's that we have some task that we want to complete in the world. Maybe it's as simple as making toast. You find some bread, you slice the toast, you toast the bread, you butter the toast, what degree it is that you do, what type of bread that you use. There's some little specifics, but it's a series of instructions. And, for this evolution of a computer to come to this point has been not as exciting for the computer. And to be honest, it's been not as exciting for us from the kind of theoretical standpoint. It was one thing to build computers. It's another to miniaturize devices. It's another to build augmented realities. But for many of us in engineering, what excites us is that next frontier, kind of letting those wheels go and to let it kind of move out there and to think for itself. And so the next kind of theoretical horizons are us creating something that has its own existence and can think and be very general and, either live beside us, augment us, or have a future in and of itself. So there's a lot of questions just in the evolution of a computer to the point of artificial intelligence, but a lot of also questions about, hey, how does it work with us people in society? So the thing is, this sounds great, but it's kind of just sci-fi. And so where the science comes in is where we start to think that in all other fields, not all, but once you say a lot, we can either do some mathematical theorem proving, or we can develop a hypothesis and then design some experiment. You and I can test this experiment, like in physics. We can test for particle or wave. We could have the double slit, shoot electrons through there. If it's a particle, it's going to have one distribution of points that it scatters on this screen, or if it's waves, it has another interference pattern. We can make a hypothesis, we can make an experiment, and we can test this. And so one of the problems is many of the other sciences have been very good about that. But in artificial intelligence, we've been trying to attack this very challenging and very high level task. And we haven't really been as good at designing exactly what that experiment, that criteria is to evaluate it. How do we know if we even have it? Do we have artificial intelligence right now? So as we look back through and we think of, even to the 1950s, there's a lot of early thoughts, and I'm kind of simplifying this, but the Turing test is effectively this idea where we can have a person, and then in one room is another human, and another room is that computer. And if we had something that was artificially intelligent, we could ask it a series of questions. And if the person out there asking the questions to it can't discern from which one's which, well, then we've achieved artificial intelligence, right? But what is it? Is it just the natural language processing is so sophisticated? Is it the task and the questions that we're asking? this isn't like the double slit experiment. This isn't shooting electrons through, having two possible things and testing for these hypotheses. This is a very open-ended thing. So it started to get us to think in the area of artificial intelligence, just what is this concept of intelligence? And it's important that we understand this today throughout the rest of our talk, because if we don't have this in mind, then we're just talking about building some very task-oriented thing. And so we said intelligence. It's hard to define this general test, but it's probably people, and people are special, right? Turns out insects are intelligent. It turns out in nature, trees are intelligent. They're living organisms. They're able to move, to adapt, to change to sunlight, to allow for the amount of light to come in for day-to-day living, but also across years in order to change their genetics to be able to adapt to environments and to be able to last, tens, hundreds of years. But now you've got your watch. Your watch is an intelligent piece of something, right? Your laptop with the finger recognition, with the facial recognition, with voice and all this, that's intelligent, right? And of course, poor Wally I'm just going to keep bringing him up today. But this is the point. In existence, there are so many intelligences, and those intelligences are displayed in different ways, all the way from insects to plants to people. So what is it that we're really trying to create? And so in artificial intelligence, what we've tried to do is that we first started by really looking at some classical notions, Plato, Aristotle, and we thought, hey, maybe intelligence just deals with rational contemplation or, logic. Even Shakespeare has taken a stab at trying to tell us what intelligence is. And we've had a few more modern examples, to act purposefully and rationally, to come down here and to think maybe it's about finding or creating problems. No. It's about goal-directed adaptive behavior. But it might actually be about achieving goals across a wide range of environments. So what you start to see is that there might not just be one intelligence. And so there are some areas, and that's where not just being an engineer is nice, but being a cognitive scientist, being a psychologist and studying intelligence in humans, but also outside of humans. We've got models like Gardner's 8 intelligences that says, well, what about a linguistic intelligence or mathematical and logical intelligence, spatial, musical, kinesthetic, the body, inter and intrapersonal intelligence, naturalistic, and this doesn't even include things that we've been adding more recently, such as emotional intelligence and other things. And so all of a sudden you start to gain this appreciation that you've got this guy talking here today about artificial intelligence, but then at the same time, what is even the word artificial intelligence? So probably the responsible thing for me is just to hang up right now, to say I don't have all the answers, psychologists, cognitive scientists, computer scientists, we don't have the answers. So we're just going to, put the little flag up, call this defeat, and we're going to go home, right? That doesn't work, and it doesn't settle well with us. So even though we really have a hard time understanding some of these very basic and very primitive things, part of science is progression, and it's about the fact that we might be wrong here today, but this is the best state that we understand it in. And as we progress through time, we're able to develop a better understanding of that target that we're trying to achieve. And so if you kind of think about artificial intelligence today, you guys have all heard the words, but could you identify from artificial intelligence, if I started throwing all these terms out, which things are AI, which are old AI, which are new AI, which are the best AI? And so to let you understand kind of for this progression is I would even put back as early as the 40s with the early mathematical models of a neuron in the brain. But in the 50s is when we really started being known as a field. So start doing some math for a second, everybody. That means the talk I'm giving about today, I've been in this field for 20 years, but this field's been at least 70 years in terms of its existence. And so we had started with some concepts of symbolic reasoning. It was more logical based. It was very explicit. Everything was, unfortunately, because of that, very brittle. And we spent about 2 decades making some very fantastic advancements in first order predicate calculus. So a lot of mathematics in there, state spaces, search. But, and this is the but, we hit winter. And so in about the 70s, there was so much potential being measured in artificial intelligence that this existence between man and robot became very challenging because we put a lot of financial investment into some of AI starting to mature. A lot of money, a lot of interest went into it, and intentional or not, we oversold it. And so we went into about a decade of a cold, cold winter where nobody really wanted to put a lot of money into this. And most people that weren't dedicated for their life for this topic, it was a good time for abandonment. But as we come back, we started to develop, hey, those problems, guess what? They are problems, but we have other solutions called expert systems that would allow us to address some of those things that the symbolic reasoning weren't allowing us to do. And you know what? Maybe this is the right pathway forward. Well, we made it for a little bit over a decade, and then we hit a second winter. Guess what? It's the same cycle of large financial investments into research, and they didn't pay off at the level that was expected. So this is kind of a depressing moment as seeing two winters. And then in the 90s, so this period where kind of a third generation of AI is this part where I'd enter in, where we got intelligent agents. We started with this thing called machine learning, which I'll describe more in a bit. And then now the deep learning, which is the most talked about of our technologies. And so one of the things that fears us and keeps us up at night is we're seeing this trend again in terms of investment for research programs and investment for now even industry. And with this much investment, we have never been set up this much in our life to potentially not deliver for artificial intelligence. So one of our big questions and fears are, is there just too high of an expectation, too much of a financial investment again? And have we kind of oversold this? And are we right now at the brink of getting ready to enter into this potentially third generation or third winter, as we may call it? So now maybe the slides, the topic I picked for this talk makes sense. Now, I want you to appreciate something more detailed. That's very high level and that's grand. But what really started us about 20 years ago that got AI kicked off again was really dealing with computational vision. And so the way that we had done this is we had all these wonderful theories, but now we started to look at things like the human visual system. And we look at the way that light comes in, the way that rods and cones interpret, color and intensity, the way that simple and complex cells. We understood that in the receptive fields of human vision, that you could model things with Gabor filters, so we could do signal processing. And then we understood that there was a neural system behind it that could take these electrical inputs and convert them into computational tasks for memory storage and for computing. And so somewhere deeper in your brain now, we translate those concepts through an abstractions of features, and then we can start to combine them and say, well, these types of patterns make cute little kittens, or these types of patterns somewhere else in our neural system allows us to recognize tigers if you go to the University of Missouri. So we took these understandings and we brought them back to AI, and we started to look at computational vision. And so we can now look at imagery, and we've developed a lot of sophisticated techniques, and I'll get a little bit more into them in a second, that allows us to go into an image, find things, cats, chopsticks, plates. My wife said, why don't you please pick something a little bit more serious? But if you can't laugh, you have to laugh. But we could then say the computer is now able to look at an image and say, well, this is a cat eating a dinner. And it's because we've been advancing signal image processing and natural language processing, very specific types of AI, and that it's not because it deals with magic, it's because it deals with science under the hood. And so now this is the part of the talk where we kind of shift to say, you now can appreciate some of where we've been and a little bit about where we're at, but you'd have a question for me really easy to say, so what is it now science-wise that's working for us? And this was the generation that I had moved into artificial intelligence, was that we particularly started to focus on areas called pattern recognition and machine learning. And so for a very simplification of this, I like imagery because you can think about it, but you could also imagine, DNA analysis, CPG islands. You could imagine working with acoustics and audio signal processing. I'm just picking imagery because we can all see it. But I look at an image and I can extract features, and we'd extract features from any of these domains that we're dealing with. I might measure something like length and color. And so in one domain, or the x-axis here, I get some feature amount of length. On the other domain, I get some feature amount for color. And so if I look at something like cats, cats probably are different size. They have maybe different colors than bananas. I hope cats and bananas don't look too much alike. But what we're able to do is that we can equate observations in the universe to samples in some Cartesian mathematical space. And so now all the cats show up as little black dots here. All of the bananas show up as little white circles. And what we're doing is that we're equating all of our observable universe into samples in some space. And so this is the process of looking for patterns. And the machine learning aspect is how we train a machine to become aware of these concepts. So for a task like classification, we want to somehow separate cats from bananas, you know. But what is a machine? What is artificial intelligence here? Well, the machine learning and the pattern recognition is that red line. It is the thing that in a high dimensional space takes samples and finds a way to separate them. So that if we're presented with a new sample out in the space, we'd say, well, it's closer to this thing and it's on this side of it, so it's a cat. Otherwise, it's over on that side, so it's a banana. And so all of our advancement really in the last 20 and 30 years has been about translating the problem domains that we work into these potentially high dimensional numeric domains. Typically, sometimes we work with things that aren't just numbers, but we work with other abstract input types. But we now come through and we say, boy, our modern artificial intelligence is really about curve fitting. Building the smart AI is about finding a red line out there that separates these things. And so most of our artificial intelligence at the date is about high dimensional polynomial fitting in sparsely sampled spaces. So this is leaving a bad taste in a lot of people's mouths, is to say, from a theoretical standpoint of artificial intelligence, this doesn't feel like our armchair sci-fi days. This feels like we might have boiled it down too much. And so there are some dangers. If cats always have on glasses and they're brown glasses and a banana doesn't have it, we give it enough data and there's brown glasses on the cat, that is a hypothesis that the machine can learn. And with the sample data that we get and the correlations, like all cats have brown glasses, the machine can learn that a cat is a cat if it has brown glasses. Nothing about the fur, nothing about the shape and the ears. And so there's been a lot of problems about our modern artificial intelligence because there's not been as much causal, you know, this causes this. It's more about correlation, statistics, and sampling. So now this brings us to the part where I'm sure everybody has pulled up something and they say, oh, deep learning, he's going to talk about deep learning tonight. But this is really our pattern recognition and machine learning that's really at one of its extreme states right now to do this task called deep learning. And it's also a task, may I remind you, I pointed out in 1943, we had the early conceptual model of a Macaulay-Pitts neuron, and that now we're just able to do things that we couldn't do in the 50s. So we got some old theory at play as well here. So to kind of show you, I like pictures. As you can see, I promised, you know, no equations, nothing else in here today. It's just all concepts. Is that when you look at a neural net, one of these deep learning structures, we may have an input, and I like pictures. That's why there's a car there. But it can, again, be data from other domains. It could be samples in situ from agriculture that we're looking at. But as I look at this, we have neurons, and these neurons are connected to the inputs. There's hundreds of millions of neurons, and they just start abstracting features from our data. They start to simplify and translate it. And as I've always said it, artificial intelligence is one of these ideas that the machine builds a way of looking at the world, and then it always transforms the world into what its expected model is, and then we operate in that space. So it's kind of scary. It doesn't see the world for what it is. It sees the world through the lens that it's developed. And once it makes this re-representational, you know, this transformation, it then goes into more basically neural nets to try to do decision making. And while I'm drawing this picture, I'd like to remind you, the machine you're looking at right here can be equated to a polynomial expression, which is just another curve fitting problem like the slide I showed right before you. So this is a graphical illustration of that machine on the last slide. So you decide which one you like more. Now, the way that it works is that we tend to have something that slides across an image. If we want to find a picture of Derek here, we're going to slide across and look for where my face is in the image. So I got to learn about what a pattern for a face is, and I got to learn how to search for it. Well, we found a while ago now, by studying a lot of human visual systems, that we can represent this through a neural network, and that we could do shared weights. We could model things like receptive fields and vision, and we could build one gigantic neural computer, which is doing pattern recognition and machine learning, and we can train a machine to do very complicated tasks, like the cat was eating dinner. Now, granted, the picture I show you on the left is nice tonight, but almost everybody's architectures, the little blurb I show you on the left is like one little box over on the right. We have hundreds of millions of parameters. And now you can understand how we have gigantic machines, and in many cases, not a lot of training data to support it. So, you know, there's a lot we can do now. And so you can start to see through my talk that we've kind of migrated from this point of the older days of knowledge representation explicitly about what we called symbolic artificial intelligence, having explicit concepts, explicit reasoning rules. And through time now, we've migrated into becoming more applied mathematicians, to looking at calculus, linear algebra, and now one of the biggest advances for us has been the adoption and integration of probability and statistics. Because as you saw in the last slides, we've been breaking problems down by sampling them, putting them into spaces, and then trying to train machines based around that information. So this almost inevitably always comes to the case of saying, oh, great, you know, this guy's telling me that there's these support vector machines, neural nets, fuzzy logic, random forest. And if you go to the internet, you're probably going to find 1,000 different AIs. And as you're looking out there, what you start to get to is you go, boy, what is the best AI? And a lot of the research projects that I've been funded on now, there's been specific questions. I have this task. Given this task, can you at least tell me which of all of these types or flavors of AI is the one that I should use and that will solve my task? And this is kind of our problem, is we get this intersection in the middle, which is the place we want to go to. But every one of these different AI technologies, many problems can be solved using many flavors of AI. So trying to figure out, you know, which of them are redundant, which one's the correct one, which one should I be using? It's very daunting, and it's one of the problems we've not been able to address so far today. I can't tell you today that if you wanted to do computer vision, that you should have the coupling of a recurrent neural net, you know, with a fuzzy logic system or whatever. We just have a lot of approaches, and we don't have theorems or statements telling us what's the best. So this gets us into what we do. We build societies. And so I'm part of the IEEE Computational Intelligence Society. So neural nets is a part of us. Fuzzy sets is another one of those. And that's the conferences that I've helped to run next year and ran last year. And then the other part of this is evolutionary computation. And we now have a transactions on AI. So we're a big field, big society, and most of our transactions are actually in the top 10 for artificial intelligence. So that's the one that I'm an associate editor for. It's, you know, it's confusing, and you go, boy, this guy's telling me we've recycled stuff from the 50s. We haven't really made a theoretical breakthrough. We got a bunch of cold winters, and we just keep throwing new ideas at it. So what really made the change? And what really made the change is, unfortunately, I wished I could tell you that it was an existence theorem. It was something else that we did that just turned the corner, but it was really big data right now. The fact that we can get so much image data, the fact that we can do things like smart cars, have them driving on the road and just be continuously collecting data, and doing things like self-supervised learning to allow the machines to kind of learn online and on the fly. We just have so much information coming at us, sometimes too much to digest. But it's been this combination of big data and high performance computing that's allowed us to take ideas that were good in the 50s and now put them to very large scales. So really, a lot of the credit doesn't come to us as theorists. It comes to just the breakthroughs right now in terms of big data and high performance computing. And please don't think I'm trying to discredit mathematics. The applied mathematics part is the part I love. And this is the part where I hope our theorems still change the course. But let's be honest, everybody mainly is looking nowadays, not because of our mathematical recent theorems, but because of the performance that we're giving on domains from large computers that can compute and train these things and the data to train them. So now today you're saying, boy, oh boy, things are getting serious. Now that you kind of know a little bit about where we came from, you're saying, I want a smart car, but it has to be able to interpret different sensors. It has to be able to do the detection of them and then also do autonomy. And this is a large part of what my research is, not for smart cars, but for autonomous vehicles and drones. The Siemens here now has actually, this is amazing, has got FDA approval for their magnetic resonance imaging, and to have AI to be adopted into healthcare settings. So you can tell the seriousness now in terms of the world adopting technologies. Smart farms and precision agriculture, being able to go out there, scan, look inside the environments, do variable pesticide spraying, you know, try to plant all the crops at just the perfect level so that they all come up at the exact same time. A lot of things that are automated now, but have to be adaptively dealt with, and we're using parts of AI to solve them. And then a large part of my research comes from the defense and technology sector. And there's many concerns about now as we turn systems online, what are we doing? As these can very much so impact human life, what do we do? So this brings me to my point today. Really, as we progress forward, using what you've seen now as our current evolution and current, this is how we're fancy, is really through machine learning and pattern recognition. In order to make these things work, we really need explanations, and we now need to hold AI to a different standard. And so when we look at an explainable AI, we can start to look at concepts like, well, what does it mean to be explainable? If we want, some smart car, should it be able to explain something to a human? If it was to take its visual data, does it need to be able to take that visual data and then to linguistically now give us back information to say the machine actually produced these statements here? A man in a black shirt is playing a guitar. Should it be able to translate what its decision is and what it believes? And should it be able to give that to a person so a person can kind of interact with it and see if it agrees with what the machine's doing and if they're going to trust the decisions that come out of that machine? Or maybe you don't need that. Maybe you don't need to have formal explanations, but yet you have an image and it said, well, there's a cat and a dog. Well, if you say, I don't trust you, you can say, why is it a cat? And then it's going to come out and say, and this has been one of the big advancements, has been able to visually back propagate information in neural nets to say, I said a cat, here's all the areas in the image that I think made a cat. Okay, so it seems to be overlaid on a cat. It seems to be kind of the belly, some area in there. The dog, there's some highlighting here around where the face is at. So it's a dog, it's on the face of the dog. It's not really looking at the body. This doesn't tell us exactly what the machine's doing, but it's suggestive and it is interpretable. And we could use this to figure out in some sense, how much do we trust the machine? So in this area that I work in, this explainable artificial intelligence, it's okay, maybe about explainable, interpretable, but boy, we like words: accountable, trustworthy, transparent, responsible. We've got all of these terms. And if you thought that we were having an identity crisis with the intelligence in the word artificial intelligence, wait till you understand how many definitions we have and how many of these are circularly defined for explanations on artificial intelligence. We love to just create a big hot mess here. So you can see a little bit further for an explanation. Think about three things. You have data. That's what we're using to train machines nowadays. Well, you can generate data explanations on just data by itself. So as you get data, you can have explanations on data. If you have different types of artificial intelligence, different mathematics, different things that we're throwing at it, each of those have a way to describe things relative to how it works. So, oh boy, we got one set of explanations about the data itself, one set of explanations about the AI before data touched it. And then when we trained it using our pattern recognition and machine learning, we built a model. It is that AI that's been instantiated by that data and it takes a certain state. So we got to have another set of explanations now that are just about the model. And so this is why the Defense Research Advanced Projects Agency, DARPA, had started to work to define specific questions. Machine, why did you do that? Why didn't you do something else? When do you succeed? When do you fail? So now we're looking at identifying specific questions to ask the machine and ways to have the machine answer those questions so we can start to figure out how much we trust and if we want to adopt these technologies. So one example that we do is that we do remote sensing. And so as we get on up there into space and we're taking pictures and looking for objects, land types, we build one AI, and it's Wally. It's smart, but it's not the uber smart AI that has every answer. So we build a different AI that operates a different way, Eva. And as we build that AI, it doesn't make the same decisions as Wally does, but it's smart, but just smart in different ways. And so until we can find that AI that is smarter than anything else, we're building individual AIs and we're fusing and combining them together to make a bigger, smarter AI as a series of collections of lesser intelligent AIs. And so we've been spending time about taking the way that the AIs work individually and taking the decisions that they make and finding ways to say, if you're looking for agricultural areas or airplanes or beaches, how could we look at statistics and information about how they make decisions individually? How about things when they come together? And we build these gigantic American flag looking photos, but you end up getting 150,000 or more of these things. So your eyes explode. And that was the one point early that we figured out that an explanation does not necessarily mean a good explanation. So then we started to spend time to make the machine to go over to summarize all of its internal explanations and to start to give natural language statements like, hey, AI 1 and 4 is all you need. You only need Wally and not Eva for finding, agricultural areas. Or most of the Wally model is in trouble because it's not been trained on much. And so you really should not trust Wally in general. Another linguistic statement that says, now that you've known these errors, go back and collect new data of this type to make Wally smarter. So we've been working on linguistically translating these machine internals and the explanations that they have into a form that's more suitable for people. So that takes me to the kind of the 6 questions I have to kind of let you guys think of things going forth. Is one of the big challenges that we face in explainable AI is, what is a good explanation? Is it to give all of the internal thinking that a machine does? Probably not. It'll overwhelm you. Is it to build statistics and to build charts and stuff? Lessen the data. It's good. Is it the natural language statements that we're generating? And what about different people? If I pulled today from online and I gave an explanation, I wonder if everybody would agree that that's an explanation that they were looking for. So we have to remember that explanations are really centric to people and specific people. And some people may want natural language statements first so that they can, at a very high level, get a clue for what's going on. But many of them, it's amazing, love to then dip into the statistics and then the raw data if they really want to trust it, or if they have to track a whole chain of evidence in terms of responsibility. The second one here is, remember who you're talking to. I'd love to have an AI that I can train, and then in a matter of 3 weeks on my high performance computers, it's got to be as smart as Einstein here. And I could ask it a beautiful question and get a beautiful answer. The problem is, the machines that we have right now are not machines that have the same capabilities as Einstein and are not being trained on the data. So they're really infant. They're not at that same maturation level. So as we start to ask questions about explanations to machines, we have to be very careful that the explanations that we're getting from them, we take with a grain of salt, and we remember just how mature that system that we're asking is. Is it a 5-year-old or is it a 40-year-old that we're asking a question from? Another one of these challenges that we face right now, I love this if you haven't heard this one before, the knowns, unknowns, and unknown unknowns, and it's the third that keeps me up at night, is we have an AI. It thinks it's brilliant. It learned from data, but not all data. We don't sample the whole universe to train everything. Instead, we're only learning from a very limited amount of information. And so we've learned a part of our brain, a part of the picture. But when we go to ask it a question, a lot of the times, if it knows the answer because that's what's been learned, it can answer us. But these machines are not smart enough to know what they don't know, and then to know the unknown unknowns, the things that they don't even know they don't even know. And so a big part of AI right now is going to have to start to embrace the fact that there's a lot of things that they can even attempt to explain, but it's going to have to do good to say, I really don't know what this is. This was really outside my scope. I'm really reaching here. But right now, the machines act blindly with this, not knowing they don't know it. And if we ask them for explanations, we're going to get the same crazy answer, which brings us into the case 4. I want to highlight this tonight because I love telling this to people because they always beat up on us AI people for stuff. But I come back at you and I say, every algorithm or every AI is perfect. It does what it's intended to do. So when you ask it a question, if you get a crazy answer back, probably the problem is that you had an expectation of something you wanted to get back as an explanation, but the reality is that you didn't use the right algorithm or you didn't train it the right way. So I'm sorry, folks, but you weren't being specific enough. So you can't stand there and ding the AI. The problem really is in the way that we're training them. So a lot of the explanations that we're going to get, we let backdoors in our AI, and they're coming out as legitimate answers from the AI. And guess what? I applaud the AI for having the intelligence to find those backdoors and those shortcuts. The last 2 I had inside here was, now that we're finding them, you go, boy, this guy just likes to talk about problems. But we're really trying to, and this is one of the large parts, is to use our flaws to make a better future. I don't want to go into a third winter. I'll still be an AI if there is a third winter, but I don't want to go into the third winter. And so by having AI where we can identify the flaws, we find these gaps. So now with the gaps, we're studying where these gaps are, and we're finding out that we weren't specific enough in the way that we trained it. Our way that we trained the machines were too vague, or the mathematics, the machine itself had too many backdoors. So we have to eliminate that or improve our training philosophies. So we got to get better at our mathematics, and we feed it in, we make a better AI, and we iterate. So if you like it or not, This is kind of a Band-Aid approach to science, but it's what we do in many fields. So we can use this to make ourselves better. And the last of the challenges that I kind of would leave people with is to think problem-specific XAI. This is the real crisis that we're having a little bit right now, is that we're making some breakthroughs. But this is going to sound to you like the different flavors of AI that I talked about earlier. If I talk about an explanation, somebody who does support vector machines, one type of an AI algorithm, usually associated very predominantly with machine learning and pattern recognition. Somebody has a technique that says, I'll give you an explanation. Then we go to the neural nets like deep learning, and somebody has GradCam and all these techniques to give visual explanations. But it's different than the first thing. And then you come into my field and you deal with infinite valued logic, and you say, well, I have a different way of explaining stuff. So we've been working on explainable logic systems and their roles in deep learning, but none of us are solving a common problem. We're just etching away at each of these little tools that we're doing. I don't know if we're making things better or not. It'd be nice to instead have something more like that Turing test, where we're trying to get something more abstract, a test that we could subject any of our types of AI to, and it can see if it could pass those. Well, when are you going to succeed? When are you going to fail? But it shouldn't be so anchored to what that technique is. So we need to not be reinventing the wheel right now as we're doing things like explanations. So kind of in the closing part of this, I like the devil's advocate. All of you might go away from today being like, oh, that artificial intelligence, it ain't so intelligent. And you have to ask yourself for a second, why do you do what you do? And so right now, maybe I wake up, get a shower, get up, shower, brush my teeth and shave. My wife said this is not valid because number one, I don't like shaving. Number two, there's no coffee before go to work. But why do you do each of these steps? Could you explain everything that you do? We ourselves do a lot that we can't explain. So I think that the explainable AI is the right way to adopt things into society and technology, but we really are setting a high bar, and we need to be careful about where that bar is set, because if we are using this for healthcare, and this is making decisions about if you have cancer or not, those are very drastic impacts that can lead to life or death situations. So kind of in wrapping up here, addressing the elephant in the room is that, yeah, we don't know everything. I'm happy to say I don't know everything because that leaves something to do tomorrow. So we really don't know what intelligence is. We're just trying to figure out what an explanation is, a good explanation, and all those challenges I was kind of talking about. But this is science. This is what we know today. I swear that part of learning today, you guys listening, is that the AI, you should care because it is impacting you now. And if it isn't impacting you now, it will impact you in the future through your healthcare, through the genetic modification in agriculture. You will be impacted by this. So you should care, and you should become literate in artificial intelligence, which is really the part of what my talk about today was understanding AI better, and then not having these facts of when we find holes, not with these financial investments and expectations, not saying AI stinks and walking away from the table, but integrating it in responsibly into our culture, avoiding that third winter and finding a way to better society and everything without going back and hitting a third winter. So for today, I'd like to say thank you very much. Hopefully some of these things made you think about these topics, and it wasn't as much of just me talking about one technology and trying to discuss to you about our newest, coolest idea in optimization or something. And I'd like to thank everybody inside my research lab, my students, postdocs, colleague here. And I thought about putting all my colleagues from the guy in the middle right there is from Australia. We work on some of the vision guided autonomy and drones and stuff with him. I thought about putting all my colleagues up here, but I got lazy. I didn't have time to go put all their faces. But my point being is thank you to everybody. I'm only as good as my laboratories and all my colleagues. So thank you for inviting me tonight. And if there's any questions, I'd be happy to field them. And I guess I'm going to give back control of my screen now.
Thank you, Professor Anderson. That was a wonderful talk. Certainly made me think. And as a reminder, if you have questions for the professor, you'll see a Q&A chat box at the bottom of your screen. Just type them in there and I will read them to him. And if you're watching on Facebook, just type your questions in the comment sections. I want to ask, before we get to the questions, you mentioned vision-guided drones. What are those exactly?
Yeah, so one of the things that we're doing in my research lab is that we have a couple funded projects to take a variety of different sensors that are optical, infrared, and other electromagnetic bands. And so we've been able to extend visibility outside of what humans can just see into seeing the Earth in the way that it is. But
I
now
see.
it presents a dilemma. You've got a drone that has super sensing capabilities. And as it's up there and working, the AI has to be able to combine information across different electromagnetic spectrums, but it has to do it relative to certain tasks. Like you're in an environment that you haven't seen before. How do you search that environment and map it, make sense of it? But the fun part is that we work with the augmented reality systems on one of these grants to then say, can I take back the AI's seeing and thinking, and can I give you an augmented existence now where you see the sensor data, you see capabilities beyond yourself, and you see what the AI sees, and that you live in this hybrid space. So there's a lot of fun topics in there.
Yeah, that's fascinating stuff. Here's a question I have as well. When do you think we'll see self-driving cars available to the public?
Okay, boy, this is when will we see them available to the public? Well, we have right now Tesla and other companies that have sensors already retrofitted onto cars and are already doing different demonstrations of vision guided, like Tesla and this company goes with optical cameras. So they actually look for 3D mapping. They look for being able to autonomously drive and navigate and sense. And they've done an amazing demonstration of different real-time, open world demonstrations. We're not the only country. There are many different companies in different countries that are actually at different levels of readiness right now and autonomy on smart cars than we are. So if you ask me, when do we think we're going to be available? The better question would be, is when am I going to feel comfortable to set in one of these vehicles and to cruise to Kansas City to watch a Mahomes game, a Chiefs game, knowing all the things I know about how you interpret LiDAR, how you will look at radar and other sensors. Can I tell the difference with an AI right now between a bump on the road or, no offense, if there's a baby out there? We don't have enough intelligence. And so I'm scared and will remain to be scared. But I also very much look forward to the concept that if we control factors, control the highways, if we try to kind of make it a simpler task, it may happen quicker than if you're asking me, am I going to allow my car to go off-road and do all this?
I'm ready to nap on my commute home each day. Just jump in
I
the back seat and let the car drive me home.
But actually, to that point, one of the things I've thought is I'm holding AI to a standard of perfection. But maybe the better question for you is, when do you think you're going to see us self-driving cars? When are they just going to be demonstrating that there's fewer wrecks using their technology than there is right now? So the bar may actually be a lot lower than my AI bar.
And it would save countless lives as well, and property damage. Got a question about, you talked about AI in medicine, the potential of it, and environmental area, agriculture. How is security keeping up with all of the applications?
Yes, so these are some good, so actually one of the things that I had done for a long time is dealt with healthcare, particularly a thing that we do at University of Missouri for elder care. And so we've been adopting and integrating sensors and artificial intelligence into letting people live longer and healthier into individual lives. And so it's been about preventative healthcare, and it's also been about, if somebody has fallen or something has happened, being able to do that. So we have a center here for integrating artificial intelligence into healthcare, particularly into elder care. But when you get to we're already doing a lot of this. We're not the only people doing it. But when you get into the security, by the security, if you mean how do you protect privacy in terms of all this, that is a wonderful question, because you could address that security in a couple of ways. One is just that the system itself is secure, so that the information that AI is receiving isn't faulty, nobody has manipulated it. And so there are questions of what almost AI do you run on the data first to make it kind of the data trustworthy before the AI even looks at it? Or does the AI have to almost look at data and say, do I trust this data coming in? Is there something maybe altered or really off? But actually, one of the exciting things about that for security is not just looking at the alteration of that data, thinking about when dealing with the security in general, how do I phrase this? See if I can find a good way to put this. not only what about the security of that, but what about the security of people for AI that's making decisions? Because as we look at AI that's being trained, there's a wonderful book, if you have not read, called The Weapons of Math Destruction. And it details a lot of utilizations of pattern recognition, machine learning, and this artificial intelligence, where we're using data to extrapolate things like, making criminal recommendations. So should somebody go to jail versus, being out on bail? And if you look at the data that they're extrapolating it from, it looks at certain demographic information, it looks at certain racial information. And if you're not careful, not just the security of the data in the system, the AI that you build itself can become a very racist and, a horrible, scary device itself. So when you look at the security, you can think of how are we defending against it, but you could also think about the information it's learned on. And if this is really a safe AI that we're going to choose to adopt and make things that, are hopefully trustworthy, are not basing on socioeconomic status and race. So yeah, there is a lot of questions here. Come into AI. It's called job security right now. It's not going away for a while.
Is there a preferred programming language for AI?
Oh yeah, I love these. So I've been through. I got my first degree in computer science and math. I got it then in computer engineering and electrical engineering. I've seen so many languages over the days. I love my Modula, I love my Fortran. I love, C assembly. We've had so many languages over the years and still do that we've always fought to say, who's going to have that language for AI? Well, right now, I hate to say this, it's really been Python. And it's been a language that I kind of had turned my back to. But what happened is that the field and companies, Google, Facebook, and others, have built gigantic things like a thing called PyTorch and TensorFlow. And these are libraries where now you can go and you can program in AI. You can create your own deep learner very easily. I say very easily. That still is a skill to be acquired. But really, Python and these languages coming out from companies. And I think I saw just recently that, who was this? I think it was Uber had just released a whole library, and I think Python and PyTorch for doing some explainable AI. So it's the first industry that's now trying to create some trustworthy codes. So please, I'm not advocating Python here today, but if you ask me if there's a language right now, there really is. And my students drug me kicking and screaming the last couple of years to use it. And don't tell them, but they were right.
You heard it here, Professor Anderson says everybody must learn Python. We have a question. What are some other ideas about how a layperson can become more educated or literate about AI besides attending talks like this or visiting the Linda Hall Library? Are there online resources?
Yeah, so there are, that's a wonderful question, because that was one of the things I tried to resonate on tonight, was not to go super in depth on one topic and put everybody to sleep, but hopefully everybody's a little bit more literate in some of the historical context where we're at and where we're going. But past that, there are now a lot from universities. I think MIT and a few places have opened up, and they actually are having their lecture series online, and they have some coursework that you can take and even get certificates. So if you're looking for completely free and open, there is a lot now on the web that are from universities, but are also from individual organizations. So there are some .orgs that will have tutorials and videos. And then we always make our research articles and things available. So if this is a question about where to go, I would always be happy if somebody was to follow up with this. I could make some recommendations of things to learn, but they're all over the internet right now, including videos. Yep. So I could give some hard examples, but off the top of my head, some lecture series from universities, some like AI.org, some different places, and yep.
And I should also add that we'll have a recording of Professor Anderson's talk available on our website as well, so you can go back and.
I know I should have, at the very end of the appendix, I should have put some, I was thinking I should probably put some additional links, so.
Well, send them to me. I can edit them in.
That's the way to do it.
The final version.
Yep. Yeah. I will edit that and send it to you and put it online.
Yeah. Be happy to do that.
Easiest way to close the loop.
How do you keep the questions and answers from multiplying exponentially? Yeah, why don't the questions become too numerous to ask and answer? And I think they mean in AI, not in the Q&A chat box.
So this has been this has been one of the things that I found out is that, I went down I didn't put in here today, but we have a big division, a separation in AI for some of us that call ourselves explainable artificial intelligence by design, which meant that we tried to pick a mathematics that we think is naturally more transparent, not opaque. But there are a lot of people that have already started with kind of a black box, a machine that has a lot of free parameters, like many of our deep learners that can be trained nowadays. And so we have divisions in us of just, we're smart because we picked the right mathematics, or we picked a general purpose machine that can be trained in different ways. But what we find out is both of us hit the same wall. We need data. Everybody loves learning from data. The learning is the thing that's helping AI advance. So for us AI by designers, using data to make it smarter or using a black box, both of us reach a point where the machine's left the control that we originally started with. It's doing things that we don't fully understand. And so to your point about the explanations becoming exponential, that really is the problem, is that you could dig in and explain things in so many different ways. And then if you think about explanations and all the combinations of explanations and the implications therefrom, I think it becomes even more critical that things like DARPA and those core XAI questions start to be things that we're identifying as a field, so that we're not just identifying every explanation that could be generated. We're following very specific questions that you in healthcare, or you in smart cars, or you in agriculture want answered. And then we have to find a way to make the AI answer those. So yeah, we need help. Otherwise, if you give us, freedom, we're going to give you more than what you want to hear.
Are there industry standards for that?
So yeah, in some areas now, say like in government sectors now, we actually have things like there is a White House AI initiative. And so there are a lot of organizations, government and so forth included, trying to look at specific type of guidelines and regulations, things that have to actually occur. So there are some bodies that are trying to make that happen. But when you look more at like, FDA, if you look at USDA and you start thinking about agriculture and healthcare, that becomes massive to do for general. So really you should look at individual organizing bodies. And right now we're going through some of these. National Science Foundation has just started to recognize national AI institutes. And they're focused on things like agriculture and other stuff. And actually one of the two things they picked was there was 5 tracks. And one of them was explanatory AI as part of it. So we're working towards it, but it's, yep.
And you can see Edward's comment there.
Yeah. Yes. Yep.
All right, we're approaching the top of the hour. So due to the time, this will probably be the last question.
Mm-hmm.
How can AI be applied to large, complex societal issues, such as climate change, regenerative, you mentioned agriculture,
Yep.
Geophysical predictions, earthquakes, weather?
So this is I guess if there was a good question to go out on, this one might be that. So if you couldn't tell through today's presentation, I have a real problem also with where we're at in artificial intelligence nowadays. The pattern recognition machine learning approach is beautiful, and I love it because I can study it, prove things around it, and develop really fancy stuff. But it is not associated with common sense reasoning. It doesn't allow us to integrate and deal with a lot of heterogeneous sources. And that's the stuff that I spend a lot of my time dealing with, is that my actual career is around data and information fusion. And so I think as you get to these bigger problems like societal issues of climate change, regenerative agriculture, we're now facing the need to deal with reasoning across multiple scales, across multiple sources. And these things just don't mesh well in terms of making little sample points in high dimensional Cartesian spaces that we can build machines around. We're really having to kind of rethink the way that we integrate different heterogeneous, multi-scale, multi-temporal data. And so in some sense, I'm excited about these challenges because I think they're going to get us closer to that kind of general purpose AI and that common sense reasoning about thinking more holistically versus just exploiting patterns and trying to find trends. So how can it be applied? Right now, one of those ideas is to make a bunch of small little pocket niche AIs. If you're dealing with something with agriculture, you have one AI that's analyzing multispectral data and making sense based on, well, what about the moisture level? What about the texture of the soil? And then you have another AI that's looking at the optimization of the tractor that's moving by and how it's dispensing those pesticides. It has to then also think about, well, what about the climate? What about the solar load that's coming out here right now? What about cloud cover? So it's a lot of micro AIs that are getting kind of integrated back into a kind of a systems level AI. And if you were to ask me personally, okay, great, I'll be quoted by this now, and then in the future, I'll come back and see if I still agree with it. I think that we're reaching an era, or we need to, of almost systems level artificial intelligence. It's no longer so much just about those little tiny toy examples that we do in my field, but it's about putting all these pieces together and thinking about them as large scale systems that operate. And that's going to require brand new theorems and brand new thinking for us to integrate, find stability, find ways to train them. So it's actually exciting, but some people are trying to kind of do a bottom up approach to this right now.
I was going to say, is that the trend now to create these systems?
The hardest thing is actually finding a trend in our field. I went from areas where I was one person in a room talking on a topic and there was maybe one other person, to now in artificial intelligence, you can find 500 papers on the same topic. So we have a lot of people in there, and trends, just ask me what's trending this week, versus what's trending for the year,
And a lot of it probably depends on funding for the research.
It really
as well.
does. And that funding, if you saw earlier, the 2 past winters were also when we peaked for funding to these super high levels. And then people said, you didn't deliver, the way that we wanted it. So yeah, a lot of it does depend on funding. And a lot of that also is, hopefully something we can live up to.
How much work is being done? We'll kind of end with this. How much work is being done in AI with private companies that haven't made their research public, and you don't really know what's going on there?
That is the hardest thing as a researcher right now, is that we've usually lived in an artificial intelligence society where we all share our academic papers in enough ways with one another. There might be certain governmental funding or something before that's prohibited certain information from coming out. But right now, I can tell you, we don't really know what Tesla is doing. They're using things called, for all of the vision guided AI, they're using a lot of systems to go through and to do self-supervised learning, machines that can train themselves on the fly. They can find examples of things where they ran through an intersection. Now they could go back and say, well, hey, it's because my AI wasn't smart enough and didn't recognize a stop sign. But there's a lot of things between the systems, the engineers that get that data, how they put it in, how they're updating their model. So there is a lot of magic going on in companies and industry right now. And it is kind of scary to know, just how far some things may be further advanced than what we really know. But I wish I could answer that question. There's a lot of exciting things. And if you hired me and a team of 400 people to tackle a topic, you can get a lot more done than what a professor and a few students gets done over a decade.
That's probably true. Well, thank you, Professor Anderson, for just a wonderful talk that it's given me a lot to think about. And I'm sure our attendees feel the same way.
Well, I'm always happy. If it didn't put people to sleep at 7 o'clock at night, that itself is a win.
Oh, I thank you. I think people are wide awake now, and we'll have to do this again and see where we are down the road with AI, where this all is leading to.
Definitely. And thank you all for having me, and thank you for listening. And it would have been even, I know, that much better had we all been in person and been able to communicate and, have after discussions, but thank you. I look forward to this. Yeah.
Yes. Thank you all for tuning in tonight. And again, visit lindahall.org for information on our other upcoming events. And don't forget about the Linda Hall Library Foundation. Your support makes all of our programs possible. So we couldn't do it without you. So thank you again, Professor, and thank you everyone, and have a great evening.
Thank you much.